We collaborate with architects usually. And yeah, you see the variety of buildings, and we'll also in this lecture we'll show you a little bit how we approach projects. But before that, we need to also inform you a little bit about the fundamentals of physics and thermodynamics to get you started on this. But let's get back. This is an image, excuse me, how New York looked at the beginning of the 20th century. This is the Flatiron Building, famous Flatiron Building, and you see back then we had like this like small or floor plans. We had shading on all windows. We had windows on both sides for cross ventilation. And then this is how New York looks today. And now what happened? So in 1930, in the 1930s, Carrier, the company Carrier, invented the air conditioning. And that basically, from then on, architects, designers, and designers became lazy, and they could design whatever building they wanted. And with the technique of air conditioning, they could create comfortable spaces in all these buildings. And now if we're looking at New York or all over the world, these buildings look mainly the same. We could look at any major city. Could also look at Harare in Zimbabwe. We also see these glass towers. And the problem with these glass towers is that without the mechanical systems, this is unlivable. You cannot survive in there. If there's a power outage and the air condition goes down, people have to exit the building immediately because you would not survive it in there. It would like boil your life. The temperatures would get so high. And we with Transsolar, we try to bring back this, what we say, climate responsive design, to bring back this idea of designing buildings for the climate and the purpose that they are helping the architects to assist. And Alejandro Aravena, who was the curator of the Venice Biennale in 2016, called Transsolar cutting edge engineering at the service of common sense. And I think it's a little bit this common sense that we're trying to bring back in the built environment. And we call this typically climate engineering. This is also, it's in our name, Transsolar KlimaEngineering. And to explain a little bit what is climate engineering, we got invited to the Venice Biennale in 2010 to create a cloud, an indoor cloud. So how do you do an indoor cloud? Well, you create a layer of cold and dry air on the bottom, and you create a layer of hot and humid, or relatively humid, hot and dry air on the top. And then you have a middle layer that is due to stratification between the cold and hot layer, and you introduce humidity, and that will, in theory, will form a cloud. So we did a bunch of tests to make this happen here in a cooling chamber, like 70 square meters cooling chamber, because it has very defined boundary conditions. And you can see here the test, there's already a cloud floating. So on the bottom is again the cold layer, and the top is the hot layer, and then we introduced the cloud. But when we came to the installation in Venice, it was a very old building with a lot of thermal mass. So all the walls were heavy, and it took a long time to heat up this space to what we needed. So in theory, we wanted to have this ramp designed by Tetsu Kondo, this ramp, and there's a cloud floating in the middle where you can walk through. But the problem, like these are the first tests, the problem with this building, as I've mentioned, was like a lot of thermal mass, not like in our cooling chamber, much bigger. So there was no cloud yet. We got the stratification, like from very hot to cold. So you can see it here with the infrared thermal camera. You can see the stratification that's there, but the cloud was like floating, like not as envisioned. So it was like just partially created. And so it took days of testing and back and forth, and the colleagues to work night shifts. But at the end, we managed to create this cloud. And those are now the official pictures from the cloud. You can see really on the bottom, no cloud. You can start walking on this ramp, and you can be above the cloud. You walk through the cloud, and you'll be above the cloud. You can look onto the cloud. Now, the question is, what have clouds to do with sustainable buildings? First of all, I would say nothing. But the exercise here was, if we can create a cloud in an indoor space, or if we can show that we can do that, we might as well be able to control the climate and comfort in indoor spaces. So this was the visualization, the message of it. But yeah, from comfortable indoor spaces, how do we design sustainable buildings? And this could be done, for example, like this. We use this hammer here, this car as our building, and we attach a PV system. We connect it to the public transport. We have a bike rack, wind turbine. We collect rainwater, and we call it a sustainable building. But nobody really questions the thing itself, the hammer. So we say, like, let's not design sustainable buildings and green buildings by gadgets. Let's design the building itself like the sailboat. We always use this as an example because every fiber of this sailboat is designed for maximum speed. And we feel like this is how our buildings should be designed, as like also to create high comfort and with very low impact on the environment. And why is this so urgent? I'm always using this graph that shows it's a timer that shows us like globally how much carbon we can still emit to that we can maintain the 1.5 degrees scenario, so that the world is not heating up the more than 1.5 degrees until 2050. And this clock shows us that we have basically only a little bit more than 6 years left in our CO2 budget globally. By then, we have to basically, or after 6 years, we should be emitting zero carbon. And this makes it clear that it's like really time to act. So we have to reduce our emissions. And of course, the building sector plays an important role here. It's like around globally 40% of the building sector is or of the global carbon emissions are by the building sector. And if we look at what, like, where in the buildings, there's like 1/3 is by embodied carbon, so the construction materials, and 2/3 is the building operation. But this is shifting. I'll get to this later. Also, the embodied carbon will become more and more important since our buildings are getting more energy efficient, and our our energy grids are getting more sustainable. And I want to end with this and hand over to Mariana after that with an image like this that we found in a magazine in Tokyo. It said, "Welcome to the breathtaking Tokyo water park, where you can wash away the pressure and the stress of the overcrowded city." And I mean, especially after COVID times, this image is just like doesn't look right for us, especially as Europeans. But it has a message. This is a water park there. And of course, we know water parks are totally inefficient. They use a lot of energy and produce a lot of carbon. But if you would see it as per person, the carbon emitted per person, it's relatively small and neglectable. So you always have to figure out what are you designing for. And the second message, obviously, we cannot, the people love this water park, so they're using it. So we cannot disconnect architectural quality from sustainability, because we can build the most sustainable building, passive house building that doesn't need energy or doesn't emit carbon. And it would still, and nobody, if nobody would use it, it would be still a waste of resources. So we have to, and this is why this is important for architecture students, architecture quality really goes hand in hand with sustainability. And I'm going to hand over to Mariana, who will tell you a little bit about the fundamentals.
All right, thank you, Felix. So I'm going to go and give a overview of some of the fundamental physics and principles behind this idea of designing sustainable buildings, designing high performance design. We will not be experts after reviewing all of this information. More importantly, it's to give as I said, an overview and to provide an exposure so that you know what principles matter. So that if you do encounter these questions and projects, you know, okay, this is maybe a reference to look back to, and this is something that you could reference. So we'll start by defining a little bit, what do we ask of buildings? As Felix said, the experience is important. So what do we need those buildings to provide so that we use them? And then thinking a little bit about how do we define a high performance building, a sustainable building? What's the energy happening in buildings, and how does that connect to how much energy we're taking from the electricity grid, how much fossil fuels we're using? And then we'll go through some projects that we've worked on and sort of apply these principles and think a little bit more about how we respond to climates. The topic of today's lecture is the introduction to climate responsive design. And then finally, just always keeping in mind, as Felix said, that sustainability cannot be stand independently from the architectural quality, from the experience that we have with buildings. So diving right in, what do we ask of buildings? If you just think about where you're sitting right now, important factors are thermal comfort. Are you too cold? Are you too hot? Visual comfort. Can you see what you're doing? Air quality. These are all fundamental needs that we ask of buildings. Oh, hang on one second. Let me just see who's admit. Looks like Mabel's joining. Great. Okay. So visual comfort. If we look at the inner part of this hemisphere, that's what we're experiencing, right? Illuminances, do we have enough light to do our tasks? That's kind of the most fundamental level of visual comfort. But then, is it comfortable light? Do we have glare? Do we have very high contrasts? Even more deeper, is this light helping us stay within our circadian rhythm and mimicking what we experience outside? And so that's kind of the subjective experience that we have with visual comfort. And then keeping in mind, we're talking about building design, right? Here on the exterior are the factors of buildings that can influence that visual comfort. So the glazing location, where are our windows? What's the building geometry? Do we have a very narrow floor plate where everybody has access to windows, or is it very deep? And do we depend on artificial lighting? Do we have shading, etc.? What are our partitions? In terms of air quality, this is so relevant now with COVID. One thing is just, do we have enough fresh air in our building? And that matters because of bioeffluence and just healthy environments in terms of infectious diseases, but also do we have enough fresh air coming in? Do we have volatile organic compounds coming off of the materials that we're using in our paints, in our here, the building components that matter are how much fresh air are we getting? So do we have natural ventilation? Do we have mechanical ventilation? And then is it intuitive to operate? Can we, even if we have these systems, do we know how to use them? And then finally, thermal comfort, right? This is maybe what we pay attention to the most sometimes, is is this building survivable? Are we going to boil in there as we might? Temperature, what's the humidity? But then there are other factors that we don't think about so much. So how much clothing are we wearing? Are we in a building in the summertime where that might be more appropriate for winter? Or what's the air velocity? Or what's our metabolic rate? Were we just running up the stairs? And so these influence our sense of comfort, which again, the common factor here with everything is that it's subjective. And the building design, not just the mechanical systems. So for example, if we have a convective system or a ventilation system, but also for the example of that cloud, right? The thermal mass, all these kind of different factors that we'll talk about today and in the coming lectures. How do these affect our thermal comfort? And just a quick example of what some of this means and how this affects the subjectivity, this amount of clothing, right? Like you could be dressed in a winter coat in summer and that might not be appropriate. Whereas maybe, you know, summer clothing would be more appropriate. And this unit captures how much clothing you're wearing. Your metabolic rate, are you taking a nap? Did you run up the stairs? Also, this has a metric that captures how much or what your temperature range might be that you tolerate. And then local discomfort. You could be in an office where technically the thermostat reads the same. You would think it would read the same, but if you're sitting next to a window with a breeze, or maybe you're sitting right next to the heater, those local factors will also influence the subjectivity of comfort. And then just opinion, right? If you take a survey and ask, do we think 21 degrees Celsius in winter is comfortable, or 24 Celsius in summer is comfortable? Different people will tell you different things. And all of this will affect, thermal comfort. So in order to try to, you see that there are all those different factors, humidity, psychology, metabolic rate, in order to concentrate these so that we can have a work with when designing buildings, instead of thinking just about air temperature, we think about operative temperature, which is really how does the temperature. And that's a combination of air temperature, which is a thermometer, and this mean radiant temperature, which is the average of all of the surface temperatures in your space. So here that you see, so here's a person standing in the room, and you have a hot surface temperature. Maybe there's a radiant wall here. You have kind of medium temperatures in your walls and in your floor, other walls and in your ceiling and the floor. And you have the average of all of those temperatures that this person is seeing. And so the operative temperature, in theory, takes also into account airspeed, but for most indoor environments, if you don't have ceiling fans or something, you could just take the average of the air temperature and the mean radiant temperature. And so what's great about an operative temperature is that it allows us to design for comfort. And so you can have different stations with the same comfort that have different air temperatures and different set points. So on the left over here, we have a quite cold air temperature. It's at 60 Fahrenheit, but we have a very high mean radiant temperature. Maybe we have that radiant heating panel, and so our temperature is comfortable. On the right, we have a higher air temperature set point, and we're not maybe intervening so much with the surface temperatures. And so the operative temperature is closer to that air temperature, but in both cases, they're the same. And this is great for how we design. Whereas in conventional buildings, maybe like those glass boxes, we need to operate our thermostats and our systems to have an air temperature that's colder. If we pay more attention to the whole building design, we can operate at air temperatures that are higher and use less energy as a consequence. And then one thing to point out is that here on the left, that metric is the percentage of predicted percentage of dissatisfaction, basically, and that's just how many people will be comfortable. And one of the metrics that we use for that is something called the predictive mean vote. And this takes into account all of the factors I mentioned before: metabolic rate, your surface temperature, how much clothing you're wearing, etc. And this is a standard, which is useful, but one thing to keep in mind is that standards are not one size fits all. And this was originally based on a set of students in a climate chamber for hour. So always to be used with a grain of salt. Another important metric or factor in comfort is adaptive comfort. So we don't necessarily expect the same temperature in buildings all year round. So if you have seasonal variation in outdoor temperature, you can expect a seasonal variation in your indoor temperature targets. This graph over here shows a psychrometric chart, which we'll show again a little bit later. But you have your operative temperature on the x-axis, or air temperature sometimes, and you have humidity on the y-axis. And this outline is from a standard called ASHRAE 55. And this shows, this is the zone, the combination of humidity and temperature that's comfortable. But now, if we change some of the factors, for example, your clothing, or maybe we increase the airspeed, that zone, that comfort criteria can shift to now include higher temperatures. So we've talked about what we ask of buildings, and we have established these subjective but very important topics of thermal comfort, visual comfort, and air quality are what we ask of buildings. And so in thinking about how do we define a sustainable building, how do we define a high performance, we're concerned about carbon emissions. And so one of the first things we think about is our buildings need to reduce the CO2 emissions, both from construction, from embodied carbon, and also the operation when it's working. But that should not come at the expense of meeting the needs of occupants. Another way to think about this is, well, here's the criteria that I want for my building. And if you have a typical building, maybe right after the 1930s, when Carrier designed the air conditioning unit, we just said, okay, these are the conditions that I want. I'm just going to connect this to my energy, to my electric grid, to my fossil fuels, maybe even district energy, and I will get those conditions. But for a high performance building, we want to design with the climate. We want to work with the climate, the context, the program to leverage passive design principles. We don't want these buildings to be spaceships. We want them to interact and be permeable to the surroundings. And with those strategies, we want to be able to design comfortable buildings. We want to meet our requirements, but we want our systems to use less energy, and maybe we want them to be smaller, maybe more simpler to operate, less complicated, and maybe even eliminate fossil fuels is the goal. So let's dive a little bit more deeply into understanding what is going on with energy in buildings. So going back to what we want of buildings, right? Here's kind of a simplified summary of the conditions that we are looking for. We have temperature, relative humidity, and this metric, this is for ventilation rate, how many air changes per hour. This is what we want of buildings. And first, before we think about the systems that we need to keep those conditions, we have to understand that buildings are not in a vacuum, they're not isolated. Energy is always going into a building, energy is always leaving a building. And there are two types of energy that we care about, is thermal energy. One is called sensible, which you'll probably hear again. And here you can think of temperature, and this you can measure with a thermometer. You can sense it with your skin. The other kind of thermal energy is latent, and here you can think humidity. And that's the energy associated with phase changes. So for example, evaporating or condensing water. And then energy moves in different ways as well. There's different methods of energy transfer in and out of a building. So first there's conduction, which is if you have two objects in physical contact, one is hotter than the other, this heat will flow. One is convection. Here maybe you can think of air moving. Hot air naturally rises, but it's any fluid whether that be air or water that's moving energy. Let's see. This person as well. All right. We also have radiation, and that's maybe something you haven't heard before, but it's super important because every single object in the universe emits radiation, electromagnetic waves. And the warmer that object is, the hotter it is. For example, we have a body temperature, we emit radiation, but the sun is so much hotter that emits much, much, much more radiation. And then finally, phase change, right? It's just converting energy from sensible energy to latent energy or the other way. So for example, if you have water that's in your hand and that water evaporates, goes from liquid to a gas, that energy for evaporation, a lot of that's coming from your hand. And so that will cool your hand in converting the energy from one form to another. So we have two types of energy, and we have four methods of energy transfer that we really care about. And so now, knowing that we have this energy that's going in and out of buildings, we need more energy to keep the desired conditions, right? And that energy is the ability to do work. It takes work to maintain our temperature and our relative humidity set points. Electricity, that can be fossil fuels or biofuels. I put that in parentheses because eventually we want to reduce that. And it can also be district energy, for example, district steam or district chilled water. And the combination of all of the energy that we're using to maintain those set points, they're called thermal loads. This Q right here, that's energy, and you'll see more of that in a second. But this is how much thermal energy we need to add or remove to our building to maintain conditions. These are our thermal loads. And then let's look into more detail for what's going in and out of a building. So across the envelope, right, we have three categories of energy flow: ventilation, infiltration, and transmission. And one important thing in designing in response to your climate is understanding, will there be a net flow of energy into the building, leaving the building, right? You have to design for heating or cooling primarily, or maybe both. So transmission, first of all, is the energy that's passing through the envelope. It can be maybe through the wall, through the window, and it's a combination of local convection, local conduction, local radiation. But this is kind of a zoomed in section, but when you zoom out, really transmission is summarized as the total thermal resistance of that envelope, wall or window, right? And we can summarize that resistance as an R value. And if we take the inverse of that, 1/R, that's called the U value. And these are terms you see a lot. For example, when you think about how much insulation you need for a building, you might think of R value or your U value. And you can calculate the total thermal resistance or total conductivity with this equation, which takes into account the local heat transfer coefficients. You don't need to know this by heart, but again, it's just so you are aware, the thickness of the layers, the thermal conductivity of each layer, and all of that to give you this U value. And then the total heat transferred is your total conductivity times the area of your envelope times the difference in temperature. One thing that might get into the way of understanding or of predicting your heat transfer is something called thermal bridges, which is when we construct an envelope, and this image over here shows a thermal imaging camera, a thermal image of a house in a cold climate. And what you can see is that the red and yellow parts of the image show greater heat loss. So ideally, we would want the whole house to be blue, meaning it's the same temperature as the exterior. We're keeping all of our heat inside. But when you see those yellow and red colors, that means that heat is escaping. And that's because, in part, of thermal bridges, where you might have insulation as seen in this section. This is, for example, a wall connected to a window. But then between the wall and the window, that frame creates a bridge where the heat can cross. And so there are ways to mitigate that by, for example, here we're looking kind of in plan view at that window. Here we have our glass, the aluminum frame, and you can add something called a thermal break, both in windows and also methods for wall construction. All right, another form of heat transfer is infiltration, and that's basically just the air leakage. You're never going to have a perfectly sealed, airtight envelope, right? Because you're constructing it in the real world. But there are ways to reduce the amount of air leakage. This is just uncontrolled air moving in and out of your building. And these are units in imperial units, but for example, we think of infiltration in terms of the volumetric flow of air per area of facade, of envelope. And so the lower that number, the less infiltration, the less uncontrolled air leakage you have in your building. And that's also a function of the amount of air, time, and the temperature difference. So the greater the temperature difference between inside and outside, and the greater the air, the more energy is uncontrollably going in and out of your building. Ventilation, on the other hand, we want ventilation, right? That's controlled air going in and out of your building. And so it's almost the exact same equation. We care about the amount of air and the temperature difference, but here it's controlled, we want it. And so there are two main ways to achieve ventilation. The easiest, which we all know, is just opening a window. And you can design for that. We can engineer this to be more deliberate in how we're achieving ventilation, but we can also have mechanical ventilation. And there are standards, for example, ASHRAE 62.1 that determines for different building types and uses, different programs, how much ventilation per person and per area do you need. All right, so here we've talked about ventilation, infiltration, and transmission as energy going in and out of the envelope, but we also have additional sensible and latent gains coming in through the windows as solar gains, and also internal gains, which is coming from people. You know, we give off heat as we're eating, as we're talking, as we're thinking, we give off heat, sensible and latent energy, but also the computers that we use, the equipments, the lights, if we have showers in our house, if we have plants, these all contribute to internal thermal energy that's being added to our space. So first, I'm going to talk about solar gains. So solar gains come in through the windows, right? And this is solar radiation that is entering our space. And the composition of the windows, first of all, the size of the windows, and is there shading in the windows, impacts how much solar radiation is coming into our space. But also the composition of the window, the type of the window is going to matter significantly. And we have a factor called the solar heat gain coefficient, which the lower this number is, so the number from 0 to 1, the lower that is, you can see the less amount of solar radiation is passing through the window. So as you go from left to right, you see that the solar heat gain coefficient decreases, and you can see this arrow over here is decreasing as well in size. More and more can be reflected outside. And so what can we do to windows to reduce that solar heat gain coefficient? So first, we can make it a double pane window as opposed to a single pane. That will help a little bit. But more importantly, we can use something called a low emissivity or low E coating. And we can also fill the cavity with argon as well. That will affect the transmission as well. But this low E coating will help reduce the solar heat gain coefficient. And even more, we can add a reflective coating to the exterior to further not let that solar radiation from even entering the glass to begin with. All of these configurations also affect what's called the long wave radiation. So you might have heard of the greenhouse effect, right? When you have a greenhouse, it's a completely glass building. They're very effective in being warm in the daytime in winter in cold climates because they let the sun come in, the solar radiation, but then they trap it because glass lets shortwave radiation, which is coming from the sun, come in, but it doesn't let long wave come out that easily. And so it traps solar radiation. And so if you have a low emissivity coating, that further traps that radiation, which can be helpful also in winter too, in cold climates for keeping that heat inside your building. These different configurations also affect transmission, right? Which we talked about earlier in this U value. And so these window configurations going from left to right increase the U value. So having double pane versus single pane, having the low E coating plus an inert gas like argon, that will further decrease the U value, which is what you want for being more insulating. And then finally, this will also affect the visible light transmittance, how much light will be allowed to pass through the glass. All right, so that's solar heat gains. We also have internal gains from occupants, and this depends a little bit on what it is that you're doing. If you're in a gym and you're running, you are going to be releasing much more sensible and latent energy than if you're sitting in this classroom right now listening to this lecture. We also have internal gains from lights, from artificial lighting, and the type of light matters, right? If you have an incandescent light bulb, this is essentially a heater that accidentally gives off light, as opposed to, for example, an LED, a light-emitting diode, which gives off much less heat for light. This watt per meter squared is a unit of power over area, which is the intensity of the energy that's given off. And then also the equipment, right? So your computers, but also maybe the projector, your phone, your kitchen, cook stove, everything gives off heat as well. Okay, so here's our building, here's our picture, and this is essentially the energy that's going in and out of the building. You'll notice these arrows all point in. That's because that's the direction of positive energy. If they were to point out, that would mean that you have negative energy. Energy is leaving your building. And we can summarize all of this energy going in and out of a building with this energy balance equation, where we have everything over here, your energy going in and out of your building expressed on the right-hand side of this equation, and your thermal loads is on the left. It's to balance that. It's the energy you need to add or remove to maintain your set points. And when we think about high-performance buildings, we want to think about this right-hand part of the equation, right? How can we decrease the total of this right-hand part of the equation? Because that's equal to your thermal loads. So if you decrease the total on the right, you're going to decrease what your building needs to do when it's connected to the grid. All right, that was a lot of material. So we're going to do a very quick activity. And I can't see you, so I don't know if this is possible. But I want you to please turn to the person to your right, or if you're on the very end, you can make a group of 3. And I want you to quickly, in 10 seconds, 15 seconds, decide which of these 2 buildings has a higher performance. So this building on the left has 7,500 megabTUs of energy per year, and this one is 2,500. MegabTUs is a unit of energy. So I'll give you 10, 15 seconds to quickly think about this. Which building has a higher performance? Which would you say, yes, this one's more sustainable? All right. Ah, are we talking about it? I can see you all now. Great. All right. So what if I told you that this building has 100,000 square feet and this one has 20,000 square feet? Same partners, think about which one has a higher performance. I'll give you 15 seconds. All right. Have we decided which one has a higher performance? All right. Well, before we decide, I'm going to introduce this idea of a normalized metric. And that's because, and this matters, for example, with rating systems and certification systems or building energy codes, it's hard to compare one building to another building to know, did we do a good job? Are we reducing our energy well? And so when we talk about normalizing metrics, it's normalizing maybe against the floor area. And so there's a term called the energy use intensity, or EUI, which is very common in our industry, which is the annual energy usage of the building divided by the floor area. And it's not a perfect metric because, for example, you can have a very, very low energy use intensity, and that could be because you're very efficient in your systems, but that could also be because you have a very, very, very big floor area of your building that's not very used. So always take this with a grain of salt, but it's a useful metric nonetheless. And so if we look at the normalized metric, this energy use intensity, in fact, if we go back to this one, we can see that, right, this large apartment building, even though it has more overall energy usage, it has a lower energy use intensity than the single family home, right? So maybe we could say, this one's more higher performance. Now, what about this one? You have this single family home that has 75 EUI versus this building that has 125. Which one has a higher performance? Which one do you think? I'll give you 15 seconds. Maybe it's a trick question. They have the same, yeah. Okay, so what if I told you this one is in New Mexico, which is a state in the US, which is very, very, very hot, and Alaska, which is a state in the US, which is very cold. So that means that we're not comparing one building that's the same to another building that's the same. So all this to say is that energy use intensity is just one part of the picture. When thinking about how well our building is performing, we can think about, okay, what's the use per person, right? As Felix said with that swimming pool, or how much carbon emissions. Think also about the embodied carbon, the cost, and also just the experience, etc. Finally, we can think also about, when we're thinking about the overall goal of reducing carbon emissions of how our building is operated, we're not just paying attention to how much electricity is used. We also need to think about where that electricity is coming from. And so we can use something called an emissions factor, which translates the energy from electricity and fuel into carbon emissions. And for example, this is in the United States, we have this agency, the Energy Information Administration, that tells you what the composition of your electricity grid is. So for this location, we know that our electricity is produced by natural gas, a little bit of coal, etc. And so we can get the overall kilograms of carbon dioxide per kilowatt hour of energy. And this is important. Now, it's also important to note that if your electricity is coming only from renewable energy, there will be no operational carbon emissions. So that's why maybe in some areas, the push for an all-electric building might not immediately be good for reducing carbon emissions, but there's the future potential to do this. All right. With that, I'm going to pass this back to Felix to talk a little bit about some projects.
Perfect. Thank you, Mariana. Are you all fresh still? I'll promise this was the hardest part.
Yeah.
We're gonna make this a little bit more visual and a little bit more. We'll show some projects where we adopted these kind of fundamentals that we learned now. And I want to start with a project in India. It's like very close to Mumbai. And it's a school for a women's college school. It's called Avasara Academy. And this is like very modern architecture. We say like that meets the vernacular design from there. We did this. Was finished in 2016. We did this together with the architects called Case Design, that are pretty active in India. But let's, how we always do when we start projects, we will look at the climate and analyze what are the local conditions. So first of all, this part of India is a very hot, humid climate. Over here. And then once we do our, we call it climate analysis, we look at dry bulb temperature, so this is air temperature, relative humidity, the wind speed locally, wind direction, the direct solar radiation, diffuse horizontal solar radiation, and the global solar radiation. We also look at radiation per facade. We can design something specifically for a specific facades, or if we need like more openings or less openings in a specific facade. Look at the cloud cover. Maybe like in this case, if there's like a rain season or it's very much the same all over the year, and we also look at obviously the rainfall. So the typical meteorological year, that's a weather data file that we can get from multiple weather stations, and it's like an hourly data of all this data that is listed here. So we get hourly data that we can then use in our simulation tools to optimize the building design. So the first one, we mentioned it earlier, we're looking at the psychrometric chart. You see here again on this axis is the temperature, and on this axis is the relative the humidity ratio, absolute humidity. And all these dots is coming from this weather file. Is basically every dot is 1 hour of the year, so it should be 8,760 hours or dots. Maybe we can count it later. But what we see here, so we have a part of the year where it's really humid, so we have high humidity ratio. And we have also a part of the year where it gets hot, where we have high temperatures, so over 30 degrees, over 35 degrees. But typically when the temperatures are very high, humidity is not that high. In this case, in the high humidity, we have around 25 degrees temperature on site. If we plot these temperatures on a different graph, just like looking all over the year, January till December, we see here the temperature swings. That's this red and orange, and we put here like an area where we would say like between 12 and 28 degrees. It's totally feasible for natural ventilation, night flushing, and night cooling potential. So in this range, we don't need any mechanical system. We can totally ventilate the air directly, and we see also here for the location Poon here that we have at the first half of the year, like we get high temperatures during the day, but we have a nice day and night swing, so we have lower temperatures at night, and then like mid of June the rain season starts. And we get like lower temperatures, but not that high swings anymore. And then in October, we get also moderate temperatures and again, higher temperature swings. This is also, this is just confirmed in the monthly rainfall. So this is the rain season starting in June, July, August, September. We have a lot of rain, we have a lot of cloud coverage. So this is the gray part here is basically the overcast sky, and the blue is the clear sky. So a lot of cloud coverage in these months. And also the humidity. We get very high humidities during this part. So like this is now relative humidity, get over 60, 80%, up to 100% humidity in this during this time of the year. So this. And then we also look at the solar radiation. This is the total solar radiation, and then it's divided per facade. So maybe we have during the summer actually not so much direct radiation on the south facade. There's more direct radiation on east and west facade throughout the whole year. Even the north facade gets in the summertime a little bit of direct radiation, which is here the yellow part. Yellow is direct. Green is diffuse radiation, and the blue part reflect from the ground reflection. So this is the typical strategy that we look at the climate at the local climate. analyze this and if you remember that hammer and the sailboat at the beginning, with this information, we tried to build a sailboat instead of a hammer. And for this particular project in India, we came up with this strategy. Spaces so the structure is all concrete, has high thermal mass, and the outer skin is basically very, let's say, open. We have just a bamboo shading. You'll see it in the picture later. And then what's important for this is like, and the lower floors is like classrooms, and in the upper floor are some dormitories for the girls' college. And what's important for learning is like one time, the first point is obviously daylight. You need sufficient daylight. You need thermal comfort. But the third big point is obviously ventilation. We need enough fresh air. And so with this strategy, we implemented an earth duct where we will bring in the air. With the earth has the advantage that the soil has an average temperature throughout the whole year. So if the average in this case is maybe 20, 25 degrees, so 20 degrees, the earth will always have 20 degrees. So we bring in the hot air, it cools down a little bit through the air duct, we bring it into the space, and then we ventilate it out through such an exhaust chimney, central chimney here, where all rooms are connected. Some are connected to the earth duct, some are just window ventilation or ventilation transfer elements here. And this exhaust duct will keep the ventilation flowing just passively without adding any mechanical equipment here. In addition to increase local comfort, we implemented the ceiling fans to increase the air velocity and make use of elevated airspeed where we just accept, or where human bodies accept, higher temperatures. And so this was the overall concept. And in addition, I'll get to in the details later on, this is not just an exhaust chimney here. This is also a solar chimney. You see that this has a solid wall back here and a glass on the front, and we'll heat up this air up here that is exiting, so we can increase the temperature, because we all know that warm air rises. So if we heat up the air up here, it will push out the air and increase or let this ventilation, this natural ventilation flowing and sucking in the air through the air duct. So a little bit more in detail on the concepts. So with the ceiling fan, Mariana has talked about it, this kind of comfort zone that we're in, that is typically the dotted line here. But with elevated airspeed, with air movement, we can increase our comfort zone to higher temperatures. So because we can just, our body can get rid of the energy by our skin. We can cool down our skin more easily, so we can accept higher air temperatures in the space. Another part, a big part of this or of the concept, is the massive ceilings and floors and some internal walls with concrete. Concrete has the advantage of has a lot of thermal mass. We're talking about heat capacity here, so this is the heat capacity describes the amount of heat required to raise the temperature of a material by 1 Kelvin. So the more thermal mass we have, the more energy can be stored in the structure before heating up the space. Here are some examples. This is if we have the same, we want to store the same energy. For example, water, you would just need such a little piece, and this would be the equivalent to 3,000 square foot, cubic foot of air. So air is obviously a very light material. If we compare building materials, for example, timber or bamboo is a very light material. Concrete is a heavy material with a lot of thermal mass. Also, rammed earth, for example, or earth has a lot of thermal mass. And the advantage of this thermal mass is that we can make use of this temperature swings. So when it's warm during the day, the thermal mass will heat up, but it will not so quickly release the energy into the space. And at night, when we have colder temperatures, we can basically flush out the energy from this thermal mass, so it can be charged again on the next day. So this is how you design with thermal mass. You take advantage of this of the temperature swings and the storage capacity of these materials. Here you see all the ceilings have a lot of thermal mass. And now let's look at the solar chimney that I mentioned here before. So what is this about? Well, the principle is basically we get there are two driving forces in air and natural ventilation. Like one is the height difference by the chimney, and the other one is the temperature difference between indoors and outdoors. And so when we look, we all know that the warm air rises up to the top. But if we have basically very similar in this climate, very similar indoor to outdoor temperatures, there's no driving force anymore. So this is why you introduce this solar chimney to make the air even hotter than the ambient temperature or the indoor temperature. You just top off the air. So this volume gets even hotter and you get this driving force. There's the equation that sits behind it. So it's like the height difference that is important and the temperature difference between indoors and outdoors. And you can see with this works also on windows. If they have just a height difference, the windows of 1 meter and a delta T of 2 Kelvin between indoors and outdoors, you would get already like 325 cubic meter per hour, and this is sufficient for 15 people, like fresh air, ventilation air for 15 people. So this is, if we look at the roof now and I zoom in, this is the solar collector. I've described it earlier. It has a glass wall behind. It's like solid. Here painted blue, here painted red, also to make this iconic part of the building. Make this really an iconic, like you see it from far away. And this will just heat up. It's like a little greenhouse in there. We'll just heat up this, and then it will pull out the air here to the top. Also, we see here we have solar thermal collectors for showers and so on, and PV for the other systems, lighting and so on. I mentioned this earth duct. It's a simple principle. We just like before construction, before building the foundation, they put in some concrete tubes here where you bring in the air, where the air will be sucked in and then be connected to the rooms. So it's a very simplified, just concrete tubes into the soil. And then later the constructed building, you see the air duct, the earth duct inlets are these round, let's say, holes here with a screen, obviously, to keep animals and dirt out. And then it's just connected to the rooms in here. We can also see again the concrete structure here, the massive ceilings, floor and ceilings. And we see already the local material, the shading, which is a bamboo shading here for this space. Also, we see a very open everything, where we can and access to daylight. Now, again, to show you how our concept, this was in 2014, our concept sketch from Transsolar. We had very limited budget on this project, or the project had a low budget, and we had very limited fees. So we did some hand sketches and explained how this should work. Here's the earth duct, it will come into the space, and then we need an opening here where we can ventilate in this shaft. We have the ceiling fans. We have the windows to open. And this is the build project. We have the inlet down here. You see this part, inlet and from the earth duct, and this part up here is basically the return into the shaft, ceiling fans, daylight, all windows to open. This is the same picture a little bit closer that you can see. So that the concept became reality also for the dorm rooms for the students. We had this buffer zone, then we have a transfer vent, we have like a mixing here, and then we exhaust into this chimney. Here's the upper parts are the transfers. And also here, ceiling fans. You see it up here, it's running to increase the elevated airspeed. A few other pictures just to see how this combination of modern architecture, concrete, and the local materials combined on the project. Again, here, this is basically the vent to go into the central chimney, integrated in some furniture. You see the students here, a lot of daylight. Again, here shading, also double height spaces, pretty open, a lot of light for really a great environmental quality. Here also higher spaces. We can see here all windows operable on the top, bottom for natural ventilation. So in conclusion, this project really was, the idea was to reduce first costs. Obviously, there was no mechanical engineer needed because there's basically no mechanical systems. The rooftop photovoltaic and the solar panels produce 85% of the building's energy. This is measured. Mentioned the no engineer and no equipment for HVAC required, and 80% operational energy cost saving compared to a traditional building or a conventional building. And a little fun fact, so it's been in operation for a while now, and everyone is super happy, no complaints, climate is good, comfort is good. They just complain a little bit about the noise, because obviously this chimney here connects all spaces, but the girls here reported that they use this chimney here to communicate from room to room, even over floors. So it's like a little fun fact. So they enjoy the building very much. And here another image really in this landscape, the iconic solar chimneys that we can see here. Okay, I want to talk about another a project in Africa that we did a few years back. It's a hospital in Rwanda. And this was done with, the architect was Mass Design, one of our first projects with them. They've done a lot of projects in Africa. We've been involved in a few more with them over the years. But this project it was kind of the first one, and it was specifically for tuberculosis patients, so air movement, air velocity, air change rate was very important. The World Health Organization recommends a 10 to 12 air change per hour to provide a good protection. And typically 10 to 12 air changes traditionally can only be achieved by mechanical systems. But that's obviously a problem for rural areas where the power goes off or there's just not enough diesel or anything available. So we said, like, we need to achieve this naturally, the 10 to 12 air changes without any mechanical system. And it was a big advantage that this hospital, the site, was on sort of a hill. You can see it here. So a little bit exposed. So we had a lot of wind coming from basically from down from the hill going through the building. So we designed these patient rooms that are here exposed basically to the hillside, so we could make use of this natural ventilation. And obviously this will never be possible with just a like single side ventilation. You will need cross ventilation, and you need this height difference, because besides the temperature difference and the wind velocity, obviously this height difference matters when you want to achieve high ventilation rates. So in the spaces, there are also some office spaces and that are not like that are you know, they don't require this or don't have this high ventilation requirement, but the patient's room are up here where we get the ventilation, and then this was the basically the exterior circulation that the personnel and doctors would not come in contact with the patients if they don't want to. So this it gets flushed, and there was also some ultraviolet lights installed. On top, the ceiling fan really, we added this one to really help with the mixing, that we don't get any dead spots of air movement in this building. And if you look at the interior, you can see it now. Windows on the lower part and the windows on the top part, and yeah, just a great advantage here. Achieving such a hospital in a rural area is just by natural ventilation. You can see it here again. Windows up here. Low costs, obviously, which is important, and maintenance fee. I mean, this is the next part that these mechanical systems break, and therefore the ventilation system is a great approach here. We can also see very friendly light lit rooms. The white paint, obviously, the windows on both sides help with the daylight as well. So another great achievement here for this building. And also, this is now, you can see here this exposed situation. The building was constructed with local materials, using local craftsmanship. I think that's very important, and ensuring a high level of ownership from the community. And they call it their little castle up there on the hill. So it's a very good story, especially that it was so well achieved by the community. Jumping to another project, colder climate. We're in Germany now. That's a building that we did 2 years back, or was completed 2 years back. It's called Alnatura Campus in Germany. Alnatura is a organic manufacturer, like of organic food manufacturer, and this is their headquarters. And the idea here was also to design a high performance building, but as I've mentioned in earlier, the embodied carbon plays a more and more important role, and this was done here. The goal was to use rammed earth as a facade material. You can see it here already. This is rammed earth, and the reason for this is, especially in let's say Europe and the United States, there's a trend of buildings. This is all buildings, office buildings, residential buildings. You can go through everything. Red is embodied carbon. This is what the standard is, and blue is the operational carbon. So what we need for heating, cooling, lighting, and so on. So in an existing standard, the operational carbon was much more than the embodied carbon. New standard, it's shifting because the operational carbon goes down, because we can design now more energy efficient buildings. But new advanced, the operational carbon gets more down, and we're shifting much more of the carbon emissions to the embodied carbon. Also because we need more insulation materials, or more insulation. but also because our energy grid gets more and more renewable, and therefore the operational carbon gets lower. So there's a trend. This is just the percentage. It goes to a trend to almost 50% now, that it's 50-50 of a building over a whole life cycle. And this trend will go higher and higher the more renewables we have in our grid. So this was the goal here, to use materials, local materials, but also the overall climate concept was pretty ambitious. We have also in this one an earth duct where we bring in supply air. We have operable windows, obviously, and the client they didn't want to have, like, should be all very open, and they didn't want to have like heating or mechanical systems in their floor plan. So we said, like, okay, an option is we add to this rammed earth wall, we add a radiant heating and cooling function. So there's tubes embedded in the rammed earth, so that we have a wall heater basically, or cooling over the wall to the space. Also, obviously, the skylight here oriented to the north, so we don't get a lot of direct light, but direct radiation, but we get a lot of daylight. It has a geothermal field. We're using the energy from the soil as a renewable energy source. And it was also a lot talked about this adaptive comfort, that we can extend the comfort range. Here's a picture, because this is really the main focus of this rammed earth wall. This was not built by hand. This is an industrial process. We have obviously the soil, the earth, and we included a layer of an insulation layer. This is foam glass in this case, because it's a cold climate, so we need a little bit of insulation in the wall. And you see this kind of machines that are basically ramming the earth on industrial scale. And then, but this was on site, next to the site, basically a big tent where they built this prefab facade blocks here. You can see this little white tubes that you can see here is the radiant system here on the inner part of the wall that would help with the heating and cooling of the building. So they're all manufactured on site and then basically put in place, stacked on top of each other. And this is the final result. You see here the facade, very simple. These elements stacked on top of each other. Inside, you have this nice rammed earth combined with timber frame and a concrete ceiling. The ceiling has the stripes that you see here as some sound measures to reduce the acoustics in there. And spaces are very open, just separated by curtains. Another view here you see inside the building, we have this large glass facades to the east and west, which is for views, really, to have the connection to the outside for the people that work here, very well lit, and a lot of and very open space. Another image you can see here, great example. My next example is in the United States. It's in Pennsylvania, which is still, I would say, on the East Coast. It's a visual art building for the Franklin and Marshall College, for a college there. We did this together with Stephen Hall Architects. And you see, this is the building that is kind of floating in the trees here on the campus, in this existing beautiful trees. And this was also kind of the vision of Stephen Hall, of the architect. This was one of his first sketches. So he basically used the trees, the diameters of the trees to shape the floor plan. Up here is the floor plan. But he also used the diameters of the trees to shape the roof here. So he got us on board to this project, and he said, like, okay, I have this beautiful site that actually there was an existing building and had to be teared down, and then this one built just within the trees. All the trees should be kept on site. We made an energy concept for that. We said, like, okay, we can activate the floor, the concrete there for floor heating. Or radiant slab. We can do displacement ventilation from the bottom, from above. This is the winter concept. There's some like some ventilation ducts here and there, but it obviously the systems should be very minimized so we don't see them. And in the summer, we can use this radiant floor for cooling. So those are just tubes, plastic tubes in the concrete where we run cold and warm water through. And also, there was the idea of we have this double height studio spaces, art studio spaces for the students. So if we have again this height difference, we first of all don't need to condition the whole space. It needs to be conditioned where the people are down here. And we can also, again, take advantage of this height difference for a natural ventilation approach. And so we looked at the climate, at the weather data again of Pennsylvania, and they were like, oh, it's humid here, it's hot here, and we cannot do natural ventilation. And then we said, like, okay, if we keep the temperature between 50 and 79, it's like a little extended Fahrenheit temperature range, and the humidity limited, we have a potential of almost half the year during operation where we can ventilate this building naturally. These are the green dots that we see here. Obviously, in the peak summer when it's hot and humid, we cannot ventilate naturally. And in the winter when it's too cold, we cannot ventilate naturally. But in the shoulder seasons, you see here that the green dots, there's a high potential for natural ventilation. So we showed them how to do that. Those are the double height studio spaces that I mentioned already, an opening on the bottom, an opening on top. And we told them, let's make it visual for the students and the staff to explain how to use this, because you have to imagine, especially in the United States, it's not that common to use natural ventilation. Everyone is relying on mechanical systems. So we have to educate them and make indicator lights. When are the conditions good outside for natural ventilation, and when are they maybe not so good anymore, too humid, too cold, so they better should close the window. So just simple indicator lights that were implemented in the design. This is now built here, the build situation. So little indicator lights here, windows on the bottom and windows on the ceiling to ventilate the space. And it's the first building on this campus where natural ventilation became part of the ventilation concept. Although those, obviously the older buildings all were relying on natural ventilation, but I told you the story about Carrier and when they invented systems and designer became lazy, so everything is controlled mechanically now. But this is a great example here. Then another part was this facade. Stephen Hall had envisioned this translucent channel glass to build this round shape. So every glass is following a little bit this round shape. So it's all elements that are set in the facade like this. So he could do the curves. And he also said, like, these are art students, they should focus on their work. So we don't want a lot of views. We want a lot of daylight to that they can work on their art, but they should not be distracted by the outdoors. So they should focus on their work. So this is why it's translucent. It will you cannot see through, but it lets a lot of light in. And it's a special double layer channel glass here, which has some insulation material in there. So you get really good U values, 0.8. So it's as good as one of the like a triple glazed window. Here's an image of this. There's this kind of foam filled in here inside this glass. And then there was the question. I told them it's a lot of glass around there, and we'll probably have a lot of overheating, or we have to cool the building a lot. So the facade is like this translucent facade is a lot. And then they said like, yeah, but can we not take advantage of these trees that are there, because it's so unique that you're building a new building into an existing grown site where we have a lot of trees. So we said like, okay, let's see how we can do that. So we took the trees, the shape of the trees, and also the leaf coverage into our buildings, into our simulation, our thermal simulation, to check the thermal comfort, but also design the systems inside the spaces. So we had like different leaf coverages and the location for the spaces, so we could actually take advantage of this trees and reduce the thermal load. We together with the mechanical engineers, we really used the trees as an external shading, and so we could reduce the systems in there. Nevertheless, the daylight is just great, because there's a big advantage in the summer when you have a lot of daylight. Um, they're like in a lot of direct light. The trees have their leaves, so they protect. And in the winter, when there's not a lot of daylight and not a lot of direct sun, the trees don't have so much leaves. So overall, the overall daylight quality is very, very good in the building. You see here the studio spaces have all a daylight autonomy of over 50%, which is really a very great value, a great number here. If you see now the build project, really well lit here, a well lit space. Again, what I mentioned, no views, which was a little confusing for me at the beginning, but Stephen Hall explained it's really that they focus on their work. In the ground floor, we have some larger openings where you can enjoy and see. In the ground floor is very transparent, where you can look through the building and see the trees. But the upper floors where the studios are, they have just little windows for ventilation and little view. This is an image from a bird perspective, and you can see again here how close the trees are. And I think really also great work to make this happen without damaging these old trees that are 100 years old or older on the campus. I'm moving to my last project, which is in Singapore. Last project of today. How we time-wise we're still good. Okay. Which is in Singapore, and it's the building for the School of Design and Environment in Singapore. And this one is interesting because there was a clear vision from the client to build a building that has high comfort, but we want a net zero energy building. So the first question is, what is a net zero energy building? Well, the definition is the building has to produce its energy on its own footprint. So basically, all the energy that has been used in the building needs to be produced on its own footprint. And so there are different approaches for a low energy building design. Obviously, we could do like a closed box, like such a boat here, or more like a breathing building, like this teepee here from the Native Americans, like where we have a lot of. This one requires a lot of mechanical systems. This requires almost no mechanical systems. So when we started the design for the the Singapore building, we said like it cannot be a box, like a closed box, which is typical what the designs look over there. It needs to be open, that the air can move through with different layers, much more interesting. But it needs a big roof because the sun is very high and we need to shade the spaces and have no direct sunlight on the facade the whole year. And if we have this big roof, we need to maximize the PV production on this roof to offset basically, or to compensate the energy that we're using in the building. So this was like kind of the design, the masses and the you know, the look of the building. And then we went to the interior. Our team did different strategies of what is the right combination of overhang, external shading, internal shading, no overhang, half and half, screens, larger overhang, and we ended up, and we all compared it with you know, the percentage of operation hours, like where we exceed 29 degrees. So this is thermal comfort. We looked at the glare. Where do we exceed basically the glare issues, too much radiation on the facade, and where do we have the best daylight autonomy, the best daylight quality. Daylight autonomy is kind of a you know, a factor that gives us information how much electricity or electric artificial light do we need. With 100%, we would never need to switch on the light. With 3%, we would have to switch on 97% of the time. So with all these parameters, we came up with a design and that has an overhang, a large overhang. It has an internal screen, and it has like an operable and a part that is operable. And this is from the outside. What you see this large overhang of the building, and the spaces are here in the back. But so what about thermal comfort in the space? We had to educate them a little bit, because obviously we see the psychrometric charge again. This is somehow where we want to get in, like between 20 and 26 degrees and not so humid. So if the dots below that, we need to heat. If we have on this side dots, like hours of the year, we need to cool, and with dots up here, we have to dehumidificate. And Singapore is a very tropical climate, obviously. So we have a lot of hours up there. So there's a lot of energy that is required for dehumidification, which is very energy intensive. So if we look at the climate over the whole year, we can also describe it as a very boring climate. It's basically always between 25 and 33 degrees all year round, no seasons. And the humidity is all year round very high, almost 20 grams per kilograms, which is very humid. So when we talk about thermal comfort, and Mariana has mentioned this already in the fundamentals, we also have to talk about shading or radiation. We have to talk about air velocity, elevated airspeed. We have to talk about the humidity levels, and we have to talk about the clothing and the activity. Are we sitting down, or we're running around, or can we change, like adapt our clothes to the seasons? So thermal comfort is definitely not just air temperature. And traditionally in Singapore, as so many parts in the world, we have these glass boxes with air conditioning. So they condition the space to 24 degrees or lower, a full air conditioning. You cannot open a window. It's a box, and if the power goes off, you have to run out of the building because you'll not survive. Anyway, this is the typical. And adaptive comfort, what we say, like, is using tempered air, so we have to condition the air a little bit. We have to dehumidify it, and we use elevated airspeeds, and then we accept temperatures, operative temperatures up to 29 degrees. So this is another psychometric chart, and the purple part here is basically our comfort range. This is according to ASHRAE standard. We've mentioned this before, which is a common standard. If we put in 29 degrees air temperature, 29 degrees mean radiant temperature, so operative temperature is 29, low airspeed, humidity, and normal like sitting and summer closing, we're way out of the comfort range. This is our dot, and we're way out, unhappy faces. So if we introduce now elevated airspeed, 0.7 meters per second, just a little bit of air movement, we can bring our dot remains the same, but our comfort range is extended and is on this, we're well within the comfort range, and we fulfill basically this standard. So elevated airspeed can help us here to design for a lot like different strategies, not the full air conditioning. And this is also something that is another point. We have there was an installation on also Venice Architecture Biennale in 2014 from Rem Koolhaas, and he called it just ceiling room. And he showed in an installation, this is what we typically see in a room, and this is what is above this room, which is like probably 1 to 2 meter space here where I could walk in of mechanical systems to keep our buildings in these conditions that we want in this tight, full air conditioned systems. And this is something we applied also to the Singapore School of Design. So he said, like, this is how it looks when you have full air conditioning. You have your suspended ceiling, and there's above all the space that you cannot use. So let's do minimal air condition, bring a little bit dehumidified air in there, use the ceiling fan so we have the adapted comfort, we can increase our comfort range. We have much more floor to ceiling height, we have better daylight, we have nicer spaces, so a lot of benefits, and we can even open the windows because it will not ruin our condition, because it's just like let's say designed for higher temperatures. And with this mechanical systems that we always see here is like, in theory, this all sounds good. That could work when we do our rating systems or our when we fulfill our thermal performance. The calculated energy demand is always great, but there's what we call a performance gap, because the experience is in the built world, and there are many studies about that. Buildings just don't perform as they are designed, and that's not like an example or some like a few buildings. It's kind of the majority of the buildings. We have to accept that they don't perform as they were designed, unless we have a post-occupancy evaluation and bring them these buildings with a lot of mechanical equipment into the expected design performance. So that's another advantage to reduce mechanical systems, that the performance gap will not be as high as buildings that have obviously a lot of mechanical equipment. This is a picture now of the studio space here of the school. You have here the fixed shading. On the bottom is the operable shading. We are like still transparent, or let's say a lot of daylight. We have the ceiling fans here that we see here. There are some acoustic measures, and somewhere behind there is the soft conditioning, what we call it, not a full air conditioning, just a little bit of conditioned air. And then in the whole building, we had, this is basically all the spaces here, all in green, are designed for this like hybrid approach with ceiling fans and soft conditioning. We left one space which was the library as also an example, as a comparison, as a full air-conditioned space in there. So, but I mentioned at the beginning, there's a net energy story. So there's like, how do we do this to design such a building with still a lot of equipment to be net zero energy? Well, this is how you start. This is a reference building in Singapore. This is the energy consumption per year. And you see there's like so much for mechanical ventilation and air conditioning, cooling. And this was, we then went backwards and said, like, our PV production can guarantee 500 megawatt hours per year. So this is what we have available on the roof. And this is what the typical design looks. So we need to bring it down. So there were multiple iterations to bring it down to this point, optimizing the envelope, air conditioning system, the hybrid system, you know, using always soft conditioning, then other optimized designs. And I think that the important story is also because the whole team was on board of this idea. Everyone was motivated to achieve this goal of net zero energy. And that was kind of like, it took off like a snowball. Like the mechanical engineers came back and said, like, oh, I don't know, we might have found a more efficient system here, so let's put this in. And so the whole team was really into it and creating this kind of optimized design. Otherwise, this would have never been possible. So at the end, we have this beautiful building, beautiful views, beautiful climate concept, and measured an EOI of 65 kilowatt hours per square meter a year, a net zero energy building, 100% on-site, produced on-site. So we're coming to the end of our talk. For our lecture, we put together a few key conclusions. First one is, there's no single general approach for climate responsive design. I think you have seen this now. Every project is kind of unique. We have different climates, we have different contexts, different programs. The second one is designs for programs flexibility matters. We don't know how buildings will look in the future. But if we look back in the past, the buildings that last over hundreds of years, there were typically buildings that left enough flexibility to change maybe from an office space to a residential space, or to, I don't know, that just leaves a lot of special flexibility. And here, I feel like, especially if room height matters, because this leaves really a lot of flexibility for different programs. And then I think this came out in the presentation as well, minimizing the need for mechanical systems is totally essential. We need to simplify building construction and operation because systems do not perform as they were designed, typically. We need to reduce the energy consumption, and we need to find opportunities to build buildings that are not spaceships, that are not like separating us from the surroundings. We want to interact with the surroundings and buildings. And we mentioned this also a few times, sustainability cannot stand independent from architecture quality. I think all the examples that we showed are also showing really the architectural quality that you really want to go into this building, experience this building, see what is going on there, what is special about it. So I think that's really important. And now, I don't know if we have time for questions. I need to drink a sip.
Yes.
Thank you for listening.
Thank you.
Thank you very much, Felix and Mariana. That was amazing. I would kindly ask either Priscilla or Mr. Maniepa if you can guide the students in making some questions, maybe. And then I'm sure Felix and Mariana are happy to answer. Mr. Maniepa, we cannot hear you if you are asking something to the students because you are muted currently.
That if you have questions, you have to step close to our mic there, and then you can ask the question. I saw how many hands? Raise your hands again. Just a hand. Right, please step forward, and then you can pose your question.
We haven't heard very well the questions.
Yeah.
Okay, the question is coming now.
Okay, good afternoon, ma'am. My question was, how do you ventilate a building using earth ducts? Yes.
You mean how does it work?
Yes.
Yeah, you always need a driving force to exhaust the air, basically. The earth duct is a concept to precondition the air by using the advantages of the soil. So it needs to be in a combination with an exhaust chimney or a solar chimney, how we have shown it in the project, and it needs to be connected, basically. There needs to be a connection from earth duct to the room that you want to ventilate and then to the chimney.
So it's literally just pipes that are connected from the soil outside through to the room, then the room to the chimney, right?
It's ensuring that the air that you bring into your building is a little bit colder or warmer than the outside air temperature, depending on what you're looking for. So you're not just opening the window. It's providing a little bit of a, preconditioning of that air.
Yeah, and it's connected how you described it. Very, very simple.
Mm-hmm.
Yes, I am.
Okay. All right. Thank you. Can we have another question? Step forward. I needed to know how the connection is. Okay, can you step forward and then you can use our mic?
Good day. My question is, how does the air duct connect with the building? If you could share the cross section, for an example.
Yeah.
Let's see. Maybe like, or maybe this cross section here.
Yeah. Why are concepts like that? Because it's not so clear. Let's go on this one. So this is can you see the screen? Yeah. So here's the inlet of the earth duct somewhere. So this is taking outdoor air. It gets preconditioned, and then it's here connected just into the space. So here's basically these tubes that are connected to some kind of discharge element.
Just a vent.
It's basically just a connection. There's nothing. It could be concrete, could be a part of a furniture here that you connect to the duct.
Mm-hmm. Yeah. It's just
like you see here in the picture. It's just coming out here. Basically, the earth duct is underneath the room, and then it's just connected here. There's no special equipment or anything needed.
And then you can see the inlet right here. So you can imagine the pipes are going into the classroom, like underneath the classroom. And so the air is going under the classroom just through these ducts and then into the classroom.
Right, so are you, that's it? Okay, all right, thank you. Can we have another question?
Uh-huh.
You can step forward closer to our mic.
Good day. So for another question which is imposed while you're explaining, in that air duct, let's say function, or doesn't it seem to be like the lower part must be colder than the upper part, as it is just a simple mechanism of basic air, not using any mechanical?
I'm not 100% sure if I understood correctly, but yes, this is not using any mechanical system, the earth duct here, but you need this chimney to exhaust it. You need the height difference, and you need also the higher the temperature difference between. Otherwise, this will not run naturally. If it would, like without the exhaust, if it would just be a room, this will not drive. There will be not enough temperature difference and height difference to drive this ventilation naturally.
All right, thank you.
Right, next question. Right, just step forward.
Okay, good day. I'm not good in calculations, so I want to ask: all these calculations involved in your slide? My job as an architect, or there's a profession who do the calculations, then I have to adjust from there. Thank you.
So the question is, you as an architect, are you doing the calculations, or how do you adjust based on the results of the calculations?
Yes, is it my duty to do the calculations?
Ah,
Or there's a profession who does the calculations, and
Yeah.
maybe I will adjust my building and its
Yeah.
orientation based on those calculations.
so I think as a profession, that's the job that we do, is we do a lot of these calculations, a lot of the simulations to help provide results that can be informed in the design, that can inform the design. But I do think that as architects, it's important to, even if you don't understand the calculations or you don't do the calculations, it's important to understand the fundamental principles. Like, that's why it's so great that we're doing like a unit like this, or that you're learning like a unit like this, because you need to have the vocabulary and know what's out there, so that when somebody says, hey, you have an opportunity for natural ventilation and you need the windows to be this size and you need to have an outlet for the air to exit the space up high, you know, okay, that's because I need to have a height difference, or I need shading because, okay, that's so that we don't have so much solar radiation coming in, because that's going to increase the building energy.
Or on the opposite, if a mechanical engineer says we need a mechanical system for that, you cannot do this naturally. That you have heard this, there are principles that are just a little bit forgotten in the mechanical engineering world often. That are principles where we can use physics and thermodynamics, that you don't have to understand in detail the numbers, but you have to understand the principle that there are ways to increase natural ventilation, to use these kind of passive strategies for building design.
So yeah, that's a good question. Thank you.
Good day. I want to know, how do you warm these spaces in winter?
How to design these climates for winter, for cold climates?
Yes.
So a lot of the, I don't know if you want to,
No.
I was going to say a lot of the principles are the same. You know, if we go way back up to this energy balance equation, right? It's thinking about, do we have energy going into the building, and so we need to cool it and remove energy as we do in cold climates. And then in cold climates, all of these arrows are pointing in the opposite direction, right? So we want to minimize the energy that's being lost to the exterior, because heat goes from hot to cold. And so when you're in a cold climate, all of that heat that you're bringing into the space with people, with light, that wants to leave. And so there, maybe you want to allow more solar heat gains, for example, in winter. There, it's beneficial. You don't want to block them as much. Or you want to focus on insulation and reducing that transmission.
Yeah. Just to add, I think there's another lecture of designing for different climates, I guess, Clara. And I'm sure the colleagues in this lecture will touch different climates and show you climate responsive design for cold climates, for hot, for humid, for moderate, all the different climates. So you'll see some ideas there.
Right, any more questions? Step forward.
How are you? I'm not sure if I heard right, but I wanted to ask about the foundation. Like Mr. Felix, you said at first, you on the side, you line up the pipes that are supplying air into the building. So I just wanted to know how the foundations are sitting. The foundation of that building, how are they sitting through those pipes?
For the earth ducts, for example, this image.
Yeah, you see those pipes, right?
Yeah.
The way they are oriented, I want to know now how the foundations are passing through those.
Yeah, you see the foundation here. There are foundation elements, and there are also one on this side. So the earth ducts are in between. So typically, the earth ducts need to be designed that they're in between the foundation, obviously. But there could be also a concept not applied here, but there could be, if these are concrete earth ducts, maybe they could be part of the foundation, you know? Typically, you want to have them a little bit in the air, in the soil, not even connected to the building. So this is why they're basically under the foundation or in between the foundation.
Okay, so you said if they are concrete ducts, right, they may be used as foundations also, but these ducts, they are hollow, and so will they be able to bear all the forces that are acting on the building?
I think in this case, yes, because, well, in this case, they are not holding the forces, they're separate. You know, it's like, you can imagine it's like a bridge, like the foundations are creating a bridge over the earth ducts. So
Yeah,
yeah,
in this case, but you said they may be used
well,
as
well,
foundation, aren't you?
we need smart architects and structural engineers to make this happen. Yes.
yeah,
That it's part of the foundation.
yeah.
Why not? I mean, this is just one example of earth ducts. We also have seen a lot of earth ducts that are just like PVC pipes, like plastic pipes. They definitely don't hold the building. But if you go for some concrete already, some concrete earth duct, I think this idea of being part of the foundation is a great idea. So we just need somebody to do it.
Yeah, like if you have a crawl space under the building.
We're up for that. We just need an architect and a structural engineer to do it.
Yeah.
Okay. Thank you.
You're welcome.
Questions? Step forward. Don't be shy.
Okay. Let me just add to what Felix has been saying. Maybe I'm understanding his question about why he was thinking those earth ducts in relation to foundations. So basically, from the picture that you are seeing there, the foundations, they have a ground beam, meaning to say the earth ducts, those ones, they are just under a ground beam. So in your case in Zimbabwe, maybe you are used to that brick foundational wall which you put on top of the footing, and then you are thinking, where does the earth that go and things like that. It can still go in between. It can be either PVC, but you can support it by a ground beam on the ground, which is supported by the foundational steels, and then it still works.
All right, thank you for what you were saying. Good day. my question is, I can see you are showing us most of these buildings are double-story, three-story buildings, high-rise buildings. But looking at our economy in Zimbabwe, we are working with a very limited budget. And besides using these ways of ventilating, like window fenestrations and stuff, as a way of ventilating our structures, I can see you are using air ducts and other ways which seem to be interesting to me. Since I'm from Zimbabwe, I have never seen these things. They are new to me. But are there any other ways we can ventilate, like, for example, a simple house, besides looking at window, door openings, and not mentioning those mechanical ventilation ways of using air conditions and whatsoever? Are there any other ways?
I think there are many ways. There are many ways how you can ventilate a building. I think efficient is obviously a cross ventilation. If, like, going back to the principle of physics, cross ventilation, ventilation where you have height, double height spaces, height difference, this will drive the ventilation and increase the temperature with solar. So those are the principle to increase ventilation. If you just look at natural ventilation, if you look at wind-driven ventilation, you have to orient your building towards the windy sides. You have to allow cross ventilation. You have to build like small floor plans that you get enough ventilation. So I think there's so many ways. But it all goes back to the principles of the physics and the thermodynamics that you have to understand, like in terms of the, the methods or the principle, not in detail, but the principle, what matters.
Yeah, and the question is, do you give a pathway for air to move? If you design, even if it's a simple building and it's small, maybe 1 story, and you have a room that has no windows, there's no pathway unless you add a pathway, right? Maybe a vent to move the air, right? And even if you have a space, it doesn't have to be so high, just having a little opening low on one side, and you could even just have a little opening. I mean, the example that Felix gave earlier was 1 meter height difference. It doesn't have to be 2 or 3 meters height difference. Even if it's just 1 window, you could have like 1 opening on the bottom, 1 opening on the top, something. There's so many ways. Yeah.
Okay, I'm answered. Thank you.
Yeah, good. These are great questions. Any more questions, or are we about done? Ready for a break?
Good day, ma'am. So the question is, I've seen the cross section and I've seen that the pipes are almost level to the ground. Then the question is, what if there's flooding? Like, how will you prevent the water from entering the building through that cave or something?
So that's a very good question. And that's why it's important to, again, looking at this idea of designing a sailboat and not a Hummer, these need to be very holistic designs where you're taking into account, like everything has to be working together, and why you cannot design a building in isolation of where it is. And that's the climate, but also, you know, is it in a flood prone region? And is there a risk of flooding? And so, yeah, if that's the case, maybe you need to have the inlet. You can still have those earth ducts buried, but maybe the inlets need to be elevated above the height where the floodwaters might be, you know, or the whole building is elevated. There are many
Or
ways.
they're flooded and they drain again.
Or they're flooded and they drain again. Yeah, but that's a really good question because, yeah, that's just an example of how these are holistic designs where everything has to work together. Yeah.
This is why you cannot copy one building and put it to another place, like I've shown at the beginning with the glass boxes. But you can copy the principles and the ideas and apply it to the site where you're at and the purpose and the program.
Okay, just to add on to what Felix is saying, if you look outside the building that you are in, just as an example of how you can put an inlet which will not be affected by flooding, that building that you're in, that Delta Lecture Theatre, outside you'd see there are these maybe concrete with some mesh around it, those outside the buildings. I'm sure you can see them when you go outside that building. Though, of course, maybe they're not really earth ducts or something, but that can be another approach whereby you kind of elevate them so that they're not, there won't be water that goes inside the piping. I'm sure you understand what I'm talking about. When you go outside the building that you're in.
Yeah, if I can come in as well, perhaps just to assist the students since I moved them. If you check these steps as you are going out, you can see that there are some grills there. Can you see them? Yes. Those are ventilation grills. So under this floor that we are stepping on, it is hollow. There is a cavern underneath this theater, and it is ventilated by those apparatus that are outside. That's where the air comes in, and then it comes out through those ventilators. Yeah, so that's so for what Mr. Mandu was explaining is that if you see how elevated they are, it's already like a way of mitigating against the possibility of flooding. All right, thank you. Are there any other questions? Right, please step forward so that we can.
Okay, maybe we have a last question if we have any, and then I think we can get close to the end because we are a bit beyond our schedule. Is there any other question?
There's this particular thing about this building. Does it have anything to do with education? Because
Seems to be another one.
It is because this will be an inlet, the inlet for the air, and then that becomes the outlet. Right. Thank you. I think we have pretty much exhausted the questions.
Perfect.
If there are any questions, perhaps that will arise going forward, I'm sure we should be able to have them fielded in our next lecture.
Yeah.
Which should be next Friday. Is that right?
Yes, you can see on the screen the two emails of Felix and Mariana. If you have specific question, you can directly write them, or you can collect your question, write me an email, or in the next lecture, next Friday, we can keep some time for answering in person your question. Will be that okay?
Yes, so on our side, this side, it then leaves me to thank you, Clara. And
thank you.
Felix, Mariana, thank you for such an exciting and informative lecture. And I'm sure we are going to start seeing different designs in our design studio.
I hope so.
Yeah, that's our expectation. And Mr. Manu, thank you, and the other participants. So we surely should be more prepared next time. That's next Friday. We are going to have a mid-semester break. We'll talk about this, Clara. I will write to you. At the moment, the date is not yet that set. This mid-semester break coincides with our graduation period to allow the process to, yeah. So I'll communicate that with you so that we see when we are going to be having this break. It's normally about a week-long break where the students will be off campus.
Yeah.
So that it assists you with your scheduling.
Yeah, just please share an email with the complete date, and then I will arrange the calendar accordingly.
Sure.
Okay.
Great.
Then go ahead, Mariana.
I was going to say thank you all so much. It was such a pleasure to come into your classroom by way of the screen today. Thank you so much for your questions. They were really good questions.
Thanks a lot to everybody. Thanks also to Felix and Mariana for giving the lecture, and to all the students for attending. So.
All right.
I wish you a nice evening, and we see each other next Friday.
Yeah.
Thank you.
Goodbye, everyone.
Thank you.
Bye.